In this video, I would like to develop a model for this problem, which is a ball is dropped from the upper observation deck of CN Tower, 450 meters above the ground, and its height h above the ground is recorded at 1 second interval. Uh, so the model will be developed in Microsoft Excel sheet. Let's see the data. So here is the data for this problem. I will just copy this data and paste it in Microsoft Excel sheet. I hope this will work. Yes, it has worked. And just to control some of the fonts. Okay. So time in seconds and height in meters. And this is the experimental data as it was claimed in the textbook. And we have the ideal model for the height. So let's see whether it is different from the ideal case, and there is uh, a need for developing a new model. So for ideal case, initial height was 450, and then it is equal to the h naught. I have to fix this one, therefore I write C dollar P, yes, minus half gt squared minus 1 by 2 times g is 9.8 times t squared value. So this is how we write the square in Microsoft Excel. So 445.1. So it seems like just a rounding kind of thing. And 430, there is a difference of 1 meter. Well, there is a difference of 3 meters. There is a difference of 4 meter, and then there is 5 meters difference, and all that. So the differences, let's compute them from the ideal case. So 450, the real case minus the ideal case, uh, it is rather recommended to compare the model with the experiment. Okay. So the difference, so we can see the difference is increasing. So it means the ideal model is not valid for real problems. So let's develop the model for its height. So for this purpose, we have to first plot the data. So I select a type of graph, so scatter plot. The scatter plot has been selected, and I will provide the data. It has selected some data by default, uh, for which I disagree. So I choose by myself. So I eliminate, I remove all the series, and then I add X values. These are essentially the values of time. Must be selected from the first column, from column 1, the time column. X. And then Y values are the height values available from the experiment. So the data has been plotted. It has appeared on the chart. And for the chart, I have to add some elements. Axis titles, primary horizontal, and axis title, primary vertical. So x-axis is time, in seconds, and the vertical axis is height is in meters. Just for clarity, I improve the fonts and set this font for all the text written on the chart. It's better to move this chart to a separate sheet. And now the data series, the markers are a bit small, so I can improve their size. That's it. So this is the data plot, scatter data plot, and our objective is to look for a different model, since we found that the ideal model was predicting somewhat lower values. Ideal model was predicting uh, lower values than the experimental values. So therefore, let's select a different model. And for this purpose, I make the right click on mouse and look for the option of trend line. So add a trend line. So a trend line is a line based upon the mathematical expression. So by default, a linear line has been selected, and I can see the dotted version of it. Let me trace that one. So the straight line is here. Clearly, it is not the appropriate one. Even it is not appropriate for the ideal case. In the ideal case, we can observe that it is t squared. So which is some expression of parabola, which is second degree polynomial. So if I look for the second degree polynomial, by the way, there is the option of displaying equation on the chart. So it is here. So if I approximate the data by straight line, so this is the appropriate form. However, it seems to be deviant from the data. For some points, it is the line is above the points, data points, and for many points, it is below the data points. So we should look for a different, better model. So again, for the trend lines, the trend line, there is another option to, well, it's a kind of duplication. So format trend line. There is another option, display R squared value on chart. Actually, behind this model fitting, there is the method of least square fitting, which is a topic of statistics. Students learn that one in the first or second year of their undergraduate. So R squared value is 0.9235. As this value gets closer to 1, it means a better model has been achieved. So it is 0.9237. From mathematical point of view, this linear model for this height is fairly valid, fairly accurate. However, to this point, this is an empirical model. To get the real model, we have to associate these parameters like for the straight line, the slope and the intercept. We have to associate these models to the physically measurable quantities. So, for example, in the case of free falling, we have to associate something like with the gravity, like in the exact model, ideal model of the exact, we have half gt squared. So the coefficient of t squared is the 50% of gravity value, which is the a measurable parameter uh, when the object falls under the action of gravity. So this is the that's how we move forward for uh, developing the models. Anyway, let's look for the other problem, other model. So if I select a polynomial model, so the first option is with degree order 2. I can go for a third degree polynomial. I can go for a second degree polynomial, and also I have to ask for the printing of equation. And this is for the second degree polynomial. And if we see that here now the r square value is exactly 1. So mathematically, this is the best model for our problem. And if we see, it passes through all of the data points. Yes. So there is a straight line model and there is the second degree polynomial model. So we have the coefficient for x square, and we have the coefficient for x, uh, one with the negative sign and the other with the positive sign. And then there is the intercept value, which is around 450 for our problem. And the two factors, one with the one value minus 4.9, it seems to be the gravitational constant, half of it like in the ideal model. And the other factor with t and with the positive sign, it seems that this is the force which is opposite to the gravitational force. So the model 449.36 plus 0.460 minus 4.9 t squared. So this model that we have got from the regression analysis is different from the ideal model. However, later on, you will explore that uh, the real model in which the velocity of the object approaches a terminal velocity, it requires some other thing. So that's how we develop the models from Microsoft Excel. And let's do some more calculations like I did in the earlier one, ideal free fall problem. So I compute the slope values, which is equivalent to the average velocity in one interval. So for this case, I compute the height value at the end of time interval and at the beginning of time interval divided by the time interval a4 minus a3. And of course, the parenthesis must appear here. So this is like the average velocity in the intervals. These are the average velocities in these separate intervals. And then if I attempt slope of slope, slope of slope, so this will be the slope value, first order slope value at the end of the interval, and then the beginning of the interval divided by the time interval, which is a4 minus a3. So interestingly, this is also going to stay almost constant. So like in the earlier example, in the for ideal case, this was exactly equal to 9.8. So here it is slightly different. However, there is indication that within the numerical bounds, the slope of slope or the second order slope is going to a constant for a, a second degree polynomial approximation. So this is also evident if we carry out the first derivative for this one. So uh, it is twice of this one, and this is going to stay here. And then the second derivative will only include two times the 4.90 factor, and the slope is going to stay close to the derivative value. So that's it. That is the demonstration on model selection from Microsoft Excel. We will look into the other options in the next videos.